All right, good morning. Okay, let's continue the discussion of integral form of Maxwell equations. Now we know Maxwell equation basically is a summary of a series of experimental results, right? And then finally being creatively, mathematically, Maxwell found the predict the existence, or not predict, derived according to all these experimental results, right? And then conclude they also have another kind of current called a displacement current that could not be experimentally found. And more significantly, after the displacement current is discovered mathematically, and then the people predict the existence of electromagnetic waves. And then because this discovery, we have our today's 4G, 5G, and so on, right? Okay, in this chapter, what we are going to discuss is integral form of Faraday's law, right? Am's law, Gauss's law, and then law of conservation of charge. And finally, we make a summary of integral form of Maxwell equations. Okay, let's first take a look of Faraday's law, right? And we said this is experimentally discovered the phenomenon, and the mathematic expression is only used to describe what experimental discoveries, right? And what this Faraday's law tells us is we have this quantity. Now we understand what this quantity is, right? If we have electrical field, if we conduct a line integration, in electrical field, okay, what that is, we call electric motivated force, right? EMF, right? So the difference between EMF, and the voltage is, one is the line integration over a finite length, right? Between point A and point B, okay? So not closed loop, but EMF is the integration along a closed loop from a starting point and end at the same point, right? Okay, so that we call EMF. That is the difference. All right, then what this Faraday's law tells us is, okay, if we have a magnetic field in a magnetic field, we define a contour. Okay, we define, let's show this. If we have electrical field, then we define a contour C, okay, starting from starting point and the ending point is the same point, okay. Then what we do is we just do the integration. Okay, sorry, this is not electrical field. This is a magnetic field. Okay, this is magnetic field. Okay, so in the magnetic field, then if we change the magnetic field, okay, if we change the magnetic field by time, we have a different way we can change the magnetic field. Either we can change the field itself, or we can change the size of this contour, right? we can change the size of the contour. Then what we found is, if you do, then we found that the electrical field integration along this closed form is not equal to 0. Okay, it's not equal to 0. So this is the foundation for us to people create electrical generator and electrical motor. Right? Then how we describe this is, we have magnetic field, then we define a contour, and then over the contour we can define a surface. This surface can be an arbitrary size, as long as this is completely covered or with this opening is defined by the same contour C. Okay, by the same contour C. So the few important point from this discovery is the direction of S, the surface, and the contour C, we follow the right-hand rule. Okay, so that means the contour go by these 4 fingers. So your thumb point to the out. You see the normal direction of the surface. This is how we define the contour, the direction of contour C, and the direction of surface S. So this surface S, we have no restriction as long as the boundary of the surface is defined by the same contour C. Right? So you can have, we have a contour C, we can have a surface like this, or you can have a surface like this. Okay, this is also the result doesn't change. Okay, the result doesn't change. The third point is the C not necessarily exists. Okay, the C not necessarily exists. So not necessarily the physical contour or like a conducting wire. The C can be imaginary. Okay, it is defined in any shape you want, right? So the C can be imaginary. Okay, the minus sign. Okay, the minus sign is, the meaning is clear, right? So once the magnetic field, if you do the flux, you see, because B dot ds, we said, is something, a component normal to the surface, right? Then you do the surface integration over the whole surface, we call flux. Okay, so when this flux increase, okay, so that means from this time step, this time instant to next time instant, flux is larger than this time instant, so that means increase, right? So this EMF tends to be decreased. That means to reduce the change of magnetic field. Okay, so this is what that means. Okay, the magnetic field. So if your contour has a multiple turns, then your flux, this is the flux change with time, the dt, right? And then times the number of turns, and so that equal to the EMF we can measure. So EMF is something we can measure. Okay, so one way we can measure is if we just contour and leave a very, very small gap, I can measure the voltage across it, right? So because the integration has go most of the path, okay, so I can measure on these two ends. So we said we have two ways. We have two ways we can generate this time varying change of flux. Okay. The time varying flux, we have two ways. One way, if we define the magnetic field, is a function of time. So the magnetic field itself changes with time. Right. So magnetic field change with time. Then for example, if in this case we fix the contour, okay, let's say in this example, we have a contour is a rectangular shaped contour lay in X or Z plane, okay, one Y equal to 0, okay, or Y equal to any number because the magnetic field doesn't depend on the Y coordinate, right? Then let's do a calculation to say, let's calculate what is EMF. Okay, what is EMF? So to calculate the EMF, we first calculate the flux. Okay, this flux, so we do a dot product. We find the ds, right? We find the ds. ds, we know the direction. So we know the direction. If the contour's direction is this, okay, then we go right hand rule. The direction of n is go into the screen, right? Okay, so go into the screen. Then we calculate the flux. The flux is integration of B dot ds. Then the ds in rectangular coordinate system is in the plane deal with x and z, so it's very clear. All right, this is very clear. Okay, this is ds. Then B is given. Then we calculate this. Basically, is calculate this. All right, it's calculate this. Then we do the surface integration over dx and dz, and x in x along x-axis we change from x-axis from 0 to a, and then in z-axis from 0 to b, right? Okay, so this is we define our limit. Okay, we define our limit. Then this integration is very straightforward. So at the end, we know the flux must be a function of time. So otherwise, directivity will be 0, and the EMF will constant equal to 0. All right. Then once we had a flux, then we take directivity. Don't forget this minus sign. Then this is EMF. This is EMF. So we don't do the line integration, right? We don't do the line integration. We calculate the magnetic field flux, then we take time directivity. Right? So let's look at the other case is the magnetic field doesn't change. The magnetic field is constant. Okay, it's not function of time. But this time, let's change the area of this surface or the contour, right? The contour change, then the surface change. So you see, just now we only define the contour. Okay, this example, we only define contour, we didn't define surface. But why we take this surface integration? Why we take this surface integration? Because this is the simplest surface that cover this contour area, right? So you couldn't find simpler surface than this. Of course, we pick the simpler one. If you really like to go a challenge questions, you say, hey, I like to have a box. And then this is my surface, okay? So if this is my surface, but this is a complete surface, right? If you like to do this surface to deal with this contour, say, you must get the same result, right? Okay, so you must get some result, right? Okay. So the same as this, we assume we have this wire. Okay, say if this is a conducting wire, okay. Then I also have a sliding conductor wire. So this is sliding, I can move back and forth, or left and the right. Okay, I can move left and the right. Okay, but now I move toward right with a constant speed, v0. Okay, with constant speed. I just move with constant speed. So in this case, while I move, this aerial change, the C change, right? So the C change. So this is also a way to create the EMF, right? So this is to say, if we have a constant magnet, okay? If we have a constant magnet, but if I have a conducting, then I can rotate. I can rotate. That means the total area, the flux of the B will change, right, over the surface. So this is also a way so that's the way we create generator, right? So electrical generator. So in this case, we still calculate the flux first. Okay, then so this flux, when we substitute the integration limit along along y direction. So this is from 0 to some place. Okay, this is my starting point. YZ. Okay, so this is my starting point, right? Okay, then starting point plus constant speed times time, right? So then you can say the flux depend on time, right? Then we take derivativity of this flux with time. Don't forget the minus sign. Then we can find EMF. Okay, we can find EMF. All right, so this is the Faraday's law. Let's talk about Ohm's law. Okay, this become a little bit more complex right now. Okay, if we don't look at this, okay, don't look at this. Before we look at this, actually, this equation is what we learned, Ohm's law in high school. Right? What this is, the B we call magnetic flux density. Okay, but however, we define another quantity, H. Okay, This H we call magnetic field intensity. Okay, so this H is defined by flux density divided by a constant we call permeability. So this is just for convenience. The reason is this H, if I replace this by H, and then this, the H closed line integration directly proportional to the current, directly equal to current. Okay, and also that this quantity, it has nothing to do with material around it. Okay, so this is what we learn. However, if we keep using this, so if we only consider this part, people find the contradictory with the Faraday's law. Okay, with the Faraday's law and the current conservation law, we are discussed today, right? So therefore, Maxwell mathematically found we must add this term, this is a mathematically discovered. Okay, mathematically discovered. This term. So this term we gave a name we call displacement. So this current looks very similar to what? Very similar to Faraday's law, right? But you can see this is the electric field Faraday's law. You see, we also calculate the flux. But this flux, this quantity, we define another name. We define another quantity. This is called electric field flux density. You see, both the electrical field and the magnetic field has a quantity called flux density. And then both the electrical field and the magnetic field also has another quantity called field intensity. Now we get used to it, right? So we have B, we call flux density. D, we call flux density. This is called flux density, right? And then we have H and E, we call field intensity. Okay, right? So now we have 4 quantities to describe electromagnetic field. Okay. Now we are not surprised. You see, if magnetic field is a flux, when it changes with time, it creates something, right? Then we also expect the electrical field flux, when it changes with time, it creates something. What does it create? It creates a current, okay? If this current I call ID, then this current I call IC. IC maybe conduction current, and ID is a displacement current, right? Okay, so I like to make some notes. Okay, so I like to make some notes. The first I already mentioned. Okay, this quantity I denote by symbol H. Okay, I denote by symbol H. The current on the right hand side, so that is a free charge. The current formed by free charge. Okay, so that means this current and this current are completely independent. Okay, completely independent. You can apply your own conduction current, and also there's another displacement current. They both exist independently. Okay, so for example, I have a battery, I have a DC current flowing on the wire. Okay, but I'm exposed in electromagnetic waves because my mobile phone base station is just next to me, right? So these two, if I have electrical field change with time, transmit from the antenna, okay, then I have displacement current. But that current has nothing to do with the current on my conducting wire. Okay, so this two current is independent. Okay, then however, from time to time, how we define this current is current. If we know the charge, if we know the current density, then we do surface integration, right? Oh, I have a cross section, say a conductor. So I have a free moving charge, right? Moving in this direction, okay? Then I do the surface integration across cross section. This is a current density, okay? Then I put the current outside, okay? The current flow in this direction. This is the current, right? This is current. Current is a surface integration of charge density, right? But this quantity we said, okay, we use the symbol D. We define by, it's called the flux density, called the flux density vector. This flux density vector define displacement current. So I have to quick, because I have to stop it 10:15. I have to attend another meeting. Sorry, a conference. Okay, now we have. I don't expect you understand this most general Am's law, but you must accept it. Okay, you must accept it. So to accept it, this is a reality. So far, since the equation discovered, right, nearly 200 years, and then now counter example has been found. Okay. So let's draw some important conclusion. Okay. Important conclusion how to draw it is, let's define, we have a contour C1. This contour C1, I can define S1, right? Okay, I have C1, I have C1, I have S1. And immediate to the C1, I define C2. But the C2, if C1 in this direction and C2 in the opposite direction, okay, C2 in the opposite direction. Then this, because we all follow the right-hand rule, right? If the C1 is in this direction, this is the normal direction of the surface outward. Then C2 I define in the opposite direction. So the normal direction is also outward. I have S2. So therefore, if C1 and C2 coincide each other, so I form a complete closed surface S, right? This is a closed surface S. So closed surface S. Then we apply the general Am's law twice. One applied to C1 and S1. and another applies C2 and S2. Why I add them together? Because C1 and C2 are opposite direction, so this line integration cancel each other. Okay, cancel each other. And the second part, okay, so the second part, why I add the two surfaces, S1 and S2 together, I form a closed surface. You see the closed surface. Okay, oh, sorry. This is a closed surface. This is a closed surface. Sure, the current is also closed surface. The current is also closed surface. All right. Then this is a very, very important equation. This is a current continuity equation. Okay. Okay. The current continuity equation, how to explain that? So how to explain that? The D is dimension, okay, or you can say unit, okay. The unit for D is exactly the charge density, okay, Coulomb, okay, Coulomb per square meter, okay, Coulomb per square meter, right? So if we have a closed surface integration collect all this charge over the surface, what that is. This basically is, if this is a charge density, then this surface will be a total charge, So the total charge change with time, okay? So what it tells you is, this is current, right? This is current, you see? So I just showed this picture. This is current. Well, so it tells you how the current is created, how the current is generated. Current is generated because the charge, total amount of charge change with time. If the total amount of the charge decrease, that means next time the charge, total amount of charge is reduced, that means decrease, right? So that refers to this. If I move this minus sign on this side, that means once the charge reduces with time, the current going out, okay? You have a current, that creates current, okay? If the next time step charge is decreased, that means current go in, right? So that when charge decrease, current go out. When charge is increased, current go in. Okay, so this is what this minus sign is. And if say the charge in a certain region, doesn't change with time anymore, or is already depleted, okay, consumed out completely, okay? So that means this time derivativity equal to 0. What is the result? Current is the result. Remember, what current? The current going through a closed surface, okay? A closed surface, right? We are talking about current going through a closed surface. You have current in, you have current out. If the in equal to out, of course, this equal to 0, right? This is a closed surface. This is a closed surface. not the surface, it's a single point. Okay, so this is a closed surface. So this law is a ground parent of KCL, Kirchhoff current law. What in a network, okay? If this is network, okay, if this is network, you have current I1, current I2, current I3, and so on, right? The total current must equal to 0. Because of what? Because in the circuit theory, we assume inside this surface, there's no charge accumulated. Okay, then if no charge accumulated, the left-hand side of this equal to 0. All right, then we have a KVL. If you have a charge put inside this system, and this charge is changing with time, KVL, you have to wait for a little while. Why I ask you to wait? Because the charge will eventually be depleted, okay? But depending on the material surrounding it. If inside the conductor, the depleted very fast, you see, this is in the order of 10 to minus 6 seconds, right? And then if this is in a kind of dielectric, that's still depleted gradually, but slowly, but eventually it will go, right? Okay, so that is a current continuity equation. Now let's look back. If we didn't have the displacement current, could we find this law? No way, right? Okay. In another word, okay, if we already found this law, okay, or this law is obvious, okay, then Ampere's law is obvious. If we didn't introduce displacement current, you will find all these laws contradictory each other, right? So this is if Maxwell didn't find it, maybe some other will find it anyway, right? Okay, because this is something people already found all the rest of the things, right? Okay, then you look at the two laws we have discussed. One is the Faraday's law, one is Ampere's law. These two equations. Do you see the symmetry? Do you see the symmetry? Right? Okay. Oh, you may say, oh, in Ampere's law, we have a little bit, you see, things a little, you see, something more than Faraday's law, right? You can say yes or you can say no, okay? Because the conduction current only exists while the conductor exists, right? So in my office, in the air, we don't have conduction current, but we have electric field, we have magnetic field. If you can ignore these two equations, you can interchange each other. Okay, but of course there is a minus sign. There is a minus sign, right? We have to remember. So this, if you can ignore the existence of conduction current, that is the case in most of the time. Okay. If you couldn't ignore it, okay, that's also fine, because people can add people can add an artificial current. They call magnetic current. Okay, this magnetic current, in certain sense, we can find the equivalence, okay, of electromagnetic field in a certain boundary conditions. So we can introduce this term. So make these two equations very elegant, you see, symmetrical, all right, symmetrical. And the most important things, okay, these two equations, the most important things is it tells you the time varying magnetic field, time varying, right? Generate electrical field. And the time varying electrical field generate magnetic field. This is the most important. This is most important. All right. Okay. So the last thing is, let's look at this field distribution. The field distribution of a very, very small dipole antenna. Okay. A very small electrical conductor wire. Okay. If I feed a high frequency signal, it can generate. Okay. If I plot, this is simplified the near field. The electromagnetic field, the near antennas. Okay, near antennas. Then if this is the antenna, okay, this continuing line, field line, depict electrical field. And those dot line depict magnetic field. Then you see electrical field generate, the electrical field and the magnetic field, they are interlaced each other. Okay, so that means electrical field generate magnetic field, and the magnetic field generate electrical field. You see, they all interlace. You see, because this is direction going out, this is direction is go into the paper. So right, so interlaced interlaced electrical field. You see, this is interlaced, right? And this is interlaced, okay? This is a solution. This picture is a mathematical solution of this. We are going to discuss how to derive this solution by yourself. Okay, don't worry, don't be anxious. Okay, how we found this? We will discuss this. Okay, we will discuss this. How to find it. Okay, so we have to stop here today, and so ask one question. So ask one question. Okay, if no question, don't forget send your attendance record. Okay, on the chart. Okay, okay, goodbye. 谈一下，我现在要退出来的话，是不是有的学生他的他的 attendance 就收不到了？
对，如果还没有发的话就收不到。
所以我现在还不能退出来，是吧？
嗯，
那我要退出来了，现在特效。
好，我觉得应该差不多了。